Okay, I think now almost everybody is connected, so let's start. Hello again, thank you for being here. I'm Carlos Martinez, responsible for the training department in SODECA, and I'm with my colleague Carmen Gil, it will be the teacher, the speaker today. As you know, we are coming back with our microlearning program. These short training sessions speaking about trendy topics. And today we are talking about pressurization control systems for stairwells, lobbies, and evacuation routes. And we are focusing today in this standard EN 12101, the part 13 of speaking about design and the part 6 speaking about the kit requirements. As always, a little bit of housekeeping. You can write down all the questions you have in the panel box you have on your right. So at the end of the presentation, we will have a Q&A time. And as always, we will share with you the PDF of the presentation at the end of the same. Okay. So that's all for my part. Carmen, the floor is yours. So thank you for being here, and let's start.
Good morning, everyone, and thank you so much, Carlos, for the presentation. Let's begin with the macro-learning session. I had divided the presentation into 4 main parts. I will start with a brief introduction about the performance principle. Then I will talk about the newest standard, that is the EN Part 13 of 2022. After that, I will talk about the main difference that are with this standard and the Part 6 of 2005. And finally, I will describe the different certification tests as mentioned in Part 6 of 2022. So let's move on to the introduction. The main goal of the pressurization system is to maintain a free smoke area space. This will help people to evacuate, will support firefighters, and will protect property. To achieve this, the system will create a higher pressure in the escape route compared to the adjacent rooms. This different pressure will prevent the smoke from leaking through the door gaps and spreading inside the protected zone. So, how is the operating principle? It's based on the fact that the air will always move from high pressure zones to low pressure zones. And this phenomenon is important to prevent the smoke generated by a fire from spreading into the evacuation routes. So, for a better understanding, there are 3 typical zones identified. The zone C, which is the fire area, and it has the lowest pressure and the higher smoke concentration. Then we have zone B, which is the lobby area in front of the staircase, in the case if it's presented or not. And finally, we have zone A, which is the corresponding evacuation area, and it should remain free of smoke. So what happens in the event of fire is that we want to ensure that the smoke cannot move from zone C to zone B or even to zone A. And to achieve this, what we do is we pressurize zone A and zone B. While pressurizing, it's important to consider that the system must follow different conditions, and for this reason, it's recognized that 2 scenarios will coexist. The first scenario will be the doors closed, and the second scenario will be when these doors are open during the evacuation. So, when the staircase doors remain closed, the overpressure generated inside the staircase prevents the smoke from entering, as it naturally flows from the protected area to the unprotected area. However, there is a very important point to consider. If the pressure inside the staircase is too high, it might make it difficult for the occupants to open the doors while they are trying to evacuate. On the other hand, and during the evacuation, doors will be open. At this point, the pressure inside the staircase will tend to drop as it partially equalizes with the pressure of the unprotected zone. And this is the critical part. The system must be able to react quickly as it has to compensate for this loss of pressure, maintaining at least the minimum level required to continue preventing the smoke to spread inside the staircase. Now, let's watch a short video that shows how the pressurization system will work in a fire situation. Here it will show first the equipment that we need, which is basically the kit box PDS. We also need the control panel and the air grills and the pressure transmitter. So this process will start when the activation of the fire detection system. As soon as the smoke is detected, a signal is sent to the control panel. After that, the pressurization system will start working in the staircase and in the lobby if it's presented. Once the operation starts, the system begins to supply air inside the staircase and it creates a differential pressure that will prevent the smoke to enter to spread inside the staircase or the lobby. In the video now, we'll show what happened during the evacuation, which means the doors are open. Every time that this happens, the pressure inside the staircase will drop. However, the system is designed to react immediately to compensate for this loss of pressure, and it ensures that the pressure level will always remain high enough to stop the smoke of spreading inside the staircase or inside the lobby. So now we saw a brief introduction about how the system works. Let's move on to the newest standard, the Part 13 of 2022. These norms provide a standardized calculation methods and define the requirements for the design, installation, and the commissioning of the differential pressure systems. In addition, it introduced an important change in classification. This document recognizes only 2 classes of differential pressure systems. This simplifies the regulatory framework and makes its practical application much more easier. So the standard distinguishes only in 2 classes. There is Class 1 and Class 2. Class 1 applies in building equipped with automatic response sprinklers with a response time of 50 or less. Also when the operation temperature is 17 or below. In residential buildings, up to 40 meters in height or to those below the national defined threshold for a high-rise building. Another situation where Class 1 can be applied is in residential buildings that have at least 2 free fire compartments between the protected space and the fire area, considering that automatic closing doors are also in place. Finally, Class 1, it might also be applied if the specific authorities accept it. On the other hand, there is Class 2. In this case, this system will apply in all the cases where the conditions of Class 1 are not met, or when they are specifically required by the authorities. The design requirements of the differential pressure systems are defined basically in 2 different parameters. First, we have the pressure difference within the door close, and second, the air velocity requirements when this door opens. In both cases, Class 1 and Class 2, the required pressure difference is set as 30 pascals. The difference appears when we are looking to the air velocity through the door open. For Class 1, the requirement is at least 1 meter per second, while in Class 2 is set at 2 meters per second. Another requirement that is common for both systems is the door opening force, which must not exceed the 100 newtons. In addition to all these parameters, we also have the initial time, the operation time, and the response time requirements. Let's first look at the initiation time. This time starts when the activation system starts, which is called the T0. This period must be less than 60 seconds, and within this time, all components must be already in the correct operation position and the fan must have already started working. Now, let's go to the operation time. This also begins at the activation of the system, which means T0, but the maximum duration allowed here is 120 seconds. By the end of this time, the differential pressure system must be fully operational. And finally, there is the requirements for the response time. This time is measured when the door is closing and when the door is opening. It refers to the time that takes to reach the required targets, which are either the pressure difference when the door is closed or the air velocity when the door is open. And in both cases, the time allowed corresponds to 5 seconds. It's also important to highlight that this standard does not directly specify which spaces must be protected. Instead, provides several design examples that illustrate how the protection can be achieved. It indicates in each case which space should be pressurized and where the air release should be located. One of the cases is the protection considering only the staircase. It also can be considered the protection of the staircase and the adjacent lobby. Another option is the pressurization of the staircase together with the lift shaft. And finally, we have the option of pressurizing the staircase, the lobby, and the lift shaft all together. Now, another important aspect that is shown in these examples is the location of the air release, that is represented with number 6 in all the examples. The air release is essential for the correct implementation of the system. During the operation, we know that the air will flow from the pressurized space into the occupied areas. On the fire floor, it's important to provide an air release that will allow this air to escape outside after leaking into the non-pressurized zones. This is essential for two different reasons. The first one, it will ensure that the pressure difference between the pressurized and the non-pressurized areas is maintained when all doors are closed. And second, it will guarantee that the correct air velocity is achieved through the doorway in the scenario when the doors are open. So the air release can be installed in different locations, depending on which the areas are protected. Looking back at the previous slide, where we saw the 9 pressurization design examples, we can see how the location of the air release varies in each case. So if only the staircase is pressurized, here we have the examples, the air release can be located in the lobby, in the corridor, or even in the accommodation area. If the pressurization includes the staircase and the adjacent lobby, this air release can no longer be placed in the lobby itself, so it has to be installed, for example, in the corridor. In the scenario that we are pressurizing the staircase and the elevator shaft, the air release can be located in the lobby, in the corridor, or in the accommodation area. And finally, when the 3 spaces, staircase, lobby, and shaft are pressurized, the air release can be located in the corridor, provided that this corridor is part of the building design. Let's now turn to the spaces that can be pressurized. As we have seen, it's not always just about the protection of the staircase. In some cases, it might also be necessary to pressurize the lobby leading to the staircase. This lobby pressurization can be carried out in 2 different ways. One option is to pressurize all lobbies of the building simultaneously. And the other option is to pressurize just the lobby that is in the fire floor. In this second case, to make it possible that the pressurized system will just be in the lobby of the fire floor, a motorized damper and a differential pressure system sensor should be installed in each floor. The control of these dampers is handled by a PDS lobby control, and the operation is very straightforward. As soon as it receives the fire signal, it automatically activates the pressurization, but only in the lobby affected by the fire floor. Another important aspect in the design of these systems is the interaction between the pressurization and the doors. Let's take, for example, the final door of the staircase on the ground floor. It's true that the pressure inside the staircase will help the door to open, but it can also make it difficult for the doors to close properly when the system is working. In these cases, the solution is not to reinforce the door self-closing mechanism. Why not? Because the standard requires that when the pressurization system is not operating, the door must be able to open with the minimum force of 100 newtons. So, if we make this closing mechanism too strong, we could not meet this requirement. The solution then is consider the worst case scenario where the exit door is fully open. In other words, if we cannot guarantee that this door will remain closed, the design must take into account the conditions specified by this case. Beyond what the standard requires, there are also some technical solutions to manage this issue. There is the Box PDS Smart system that includes an algorithm that detects if the door is left open or not. And if this happens, the system temporarily will reduce the airflow, allowing the door to close on its own. And this way, the standard is met while it's maintained the protection in the evacuation routes. Now that we have a clear understanding of the requirements of the new Part 13 of 2022, let's compare it with Part 6 of 2005. Looking at 2005 version, the first thing to note is that it covers the pressurization and the depressurization. However, version 2022, it only considers the pressurization systems. Also, in Part 6, the staircase protection always consider the staircase, while in Part 13, it's not specified which areas should be protected, but it provides some examples. And in these examples, we see that the staircase is always included. Now, regarding the system, in Part 6, there are 6 classes, while in Part 13, it simplifies it and it's only considered 2 system types, Class 1 and Class 2. Now, let's look at the criteria of the air velocity through the fire door. In the version of 2005, the class A, C, D, and E consider a velocity of 0.75 meters per second. And for classes B and F, this value increased to 2 meters per second. In the version of 2022, this will include that 1 meter per second for class 1 and 2 meters per second for class 2. Regarding the pressure difference in 2005, is set to a general value of 50 pascals, where in situations where the exit door should be open, that is C, D, and E, it also has to consider and maintain the 10 pascals with the door open. Now, in the version of 2022, this parameter is standardized to a uniform value of 30 pascals. Finally, one requirement that remains the same in both versions. The maximum door opening force must be below 100 newtons. Regarding the response time, the 2005 version specified that variable speed supply fans or pressure sensor control dampers could not be used unless the system is capable of reaching more than the 90% required airflow within a maximum of 3 seconds. On the other hand, in the version of 2022, the response time is limited to 5 seconds when the door is opening and closing. However, it's clarified that this 5 seconds value is intended for account for the variations of the installation site. The reference test is the EN 12101 Part 6 of 2022 that we will see later, that it will impose a limit of 3 seconds. As we have already discussed here, there are some differences considering the exit door open. In the version of 2005, it's treated the final exit door differently depending on the system's class, if it's C, D, E, or B and F. While in the 2022 version, this approach has changed. As we saw earlier in the calculation example, if the door does not close completely, the standard will require that the minimum pressure and the air criteria to be met. And finally, and as we discussed earlier too, when we are talking about the spaces to protect, in 2025 version, the staircase protection is always considered, while in 2022 version does not directly define which areas must be protected. Now that we have reviewed the main difference between the two versions of the standard, it's worth it to highlight one point. In 2022, a new standard was also published, the Part 6. This standard no longer focuses on the installed systems. Instead, it's clearly defined the performance test applicable to differential pressure kits. This standard specified 3 main tests, which form the basis for the properly verifying and certifying kits. An important point to note here is that the Part 13 that we just saw before requires that these kits comply with this standard with the Part 6 of 2022. Now, let's move on to the first test, the functionality test, which corresponds to the dynamic test cycle. The purpose of this test is to simulate the behavior of a door between a protected space and a non-protected space, and to observe how the airflow toward the non-protected area changes as the door opens and closes. The test sequence is as follows. It starts with the door fully closed here and here. And in this case, we can see how we'll change the airflow and here how we'll change the pressure. So we have the door closed, and within 1 second, the door has to open. And it will remain open during a period of 6 seconds. When the door opens, the pressure inside the protected area will drop, causing that the airflow will increase. And within less than 3 seconds, that we have the time here, this airflow must reach the 90% of the maximum value, ensuring the effective pressurization. After these 6 seconds of the door open, now the door closes, and it does it with a period of 3 seconds. In this case, during the closing, the airflow will decrease and the pressure will rise. It will generate an overpressure peak, and this peak will have to stabilize in less than 3 seconds, ensuring that the pressure does not exceed the safe limits. This cycling of opening, holding, closing, and stabilizing is repeated 20 times for the test to be valid, ensuring that the system can correspond quickly and consistently under real evacuation conditions. Next, we have the durability test. In this test, the cycling sequence that we just saw from the functionality test, it's repeated 10,000 times on the differential pressure kit. Once these 10,000 cycles are completed, the functionality test is performed again. The purpose of this test is to verify that after a very intense use, the system will still meet the test criteria and to check any deviations from the initial performance. This will ensure that the kit can maintain its effectiveness and the reliability over the time, even after a high number of operating cycles. Finally, we have the oscillation test. The purpose of this test is to verify if the control system can remain stable when the door is open and when the door is closed repeatedly. The difference from the normal test, the one that we saw the first one, is that here there is no waiting time. The door opens and closes immediately, simulating a real evacuation and several people leaving one after the other one. The procedure is as follows. It performs 10 subtests. Each subtest has 20 opening and closing cycles are carried out in each one. So the cycles are performed under two different conditions. We have the door open to verify the airflow criteria and the door closed to check the pressure criterion. This way, it can be confirmed that even in simultaneous evacuation scenarios, the pressurization system continues to meet the required parameters. SODECA has tested the box PBS and the box PBS smart kits following the requirements of the 3 tests established in the Part 6 of 2022, which are the functionality test, the durability test, the functionality test for second time, and the oscillation test. As a result, these kits will meet the requirements of the European standard, ensuring that the pressurization system in which they are installed will maintain in the correct pressure and airflow. So now I don't know if I still have a bit of time, but I would like to do a very quickly calculation example using QuickFun. I assume that yes.
Of course, Karma, you are doing a master class, so you have 5 minutes more or 10 minutes more to show us the
try to do it.
The tool.
I just have here the QuickFun. Let me.
We are now.
Yes,
yeah.
sorry. Now, perfect. So here in QuickFun, we have the different parts, but the important one I would say is here in tools, where we have different ways of calculating. But if we go to pressurizing of the evacuation routes, we can see that we can choose the standard where are we going to calculate. We have the part 6 of 2025-26, and then we have the part 13 of 2022, which is the one that we need today. Here, as I mentioned, we can choose the class of the system, class 1 and class 2. Let's imagine that we are doing a building which has sprinklers. So it's going to be a class 1. In order to do it, we need always to put the staircase length, the width, and the total height. Why? Because that's the way that the QuickFun will calculate the leakage through the walls. So let's imagine that we put 7 in length, 3 in width, and a total height of 10 meters. It's already said that the maximum value is 30 pascals because it's what class 1 and class 2 will require. Let's imagine that we don't have an elevator emergency thing, lift, and we don't have the exit door open. So in this case, it's as easier to come here and say, okay, this is ground floor, and we have one door that is going to be open. I'm just putting 1.9 of the surface area, considering 0.8 in width and 2.1 in height. And that's going to be the imagined building that I have, just one door. But you can also put even more doors, double doors, elevator doors. So let's imagine that we have this configuration. Now, let's go to what is floor 1. We can assume that it's only one door of 1.9 again. And in this case, we have an office building. It's full of the staircase will always have the same configuration. So we can just copy paste it as much times as we want. And in this case, it will be calculated the airflow that we need for the differential pressure system, that is 30 pascals when all the doors are closed, and the airflow criteria when the velocity is 2 meters per second, that is this one. And here, I'm sorry, but we have to, if it's class 1, we have to assume that the air velocity is going to be 1 meter per second, so the airflow is going to be this one. And that's more or less what I wanted to show you today. So that's the end of the presentation.
Thank you, Karma, for this nice presentation. Let me add 2 points. We know that probably you guys in your computers are not seeing completely the QuickFun tool because it is impossible to zoom in. So probably you can review the video that will be able in a couple of minutes when we finalize the session, and you can use the quick fan and see properly what is Karma doing, because it is impossible to zoom in. The other thing is the quick fan is our calculation and selections software that is completely free. You can download it in our webpage. Okay, you look for the label software, and it's totally free. You can download it. Okay. So Karma, thank you so much for the presentation. Now it's time for the Q&A, the questions. We have already some questions, but let me, in the meanwhile, you take a sip of water if you want. I'm going to share the presentation with the people. Okay. Okay. In the meanwhile, you can write down all your questions, and we are answering in a minute. So I'm now sharing the presentation with you. I think you could download it now in the label documents. So if anybody had any problem, you can tell us, okay? And I send you again by mail or anything. So Karma, let's go to the question time. Already we have one from Nikita Solyanov. The question is how to define the amount of pressure sensors necessary to install in the stairwell. Is there a correlation between the amount of sensors and the amount of stores in the building?
That's a really good question, I would say. If we are talking about the sensors, of course, as much sensors that you put inside the staircase, the better will be the sensor response. As a rule of thumb, I would say that it's between every 3 levels we can put an activation sensor. But okay. Of course, it will depend depending on how many we want to put, how many levels do we have storage in the building. So it's a way to, yeah, like every 3 levels it's put in.
Every 3 levels, okay. Yeah. As generally speaking, every 3 levels, every 3 stores. Okay, thank you, Karma. I don't know if we have any more questions. Don't be shy. Yeah,
I just want to add a comment that if we are talking about if we are talking about the staircase, but if it's about the lobby and we want to pressurize it too, the sensor should be in every level of the lobby.
Okay. Duly note. So Karma, we have more questions. Another one from Pedro Neves. He said, good morning. I'm not sure if I understood correctly, but I believe it was mentioned that the system has to be able to drop the air velocity in order to allow the exit door to close. How does the system detect this? Drop the air velocity.
Yeah, I think that I understand it. It's the case of the example that I put, the calculation, where we could see that if the exit door is open or closed, the calculations will change. It's true that with the pressurization system, that might be that this door doesn't close because of the pressure that it's inside. So what we have to ensure is to try to close it. What we have in SODECA, it's the kit box PDS, that it has an algorithm inside that it already knows that, and it will let the airflow to reduce in order to provide the space for the door to close. But that is something that is inside the equipment, and I'm not 100% sure of how they design it.
Okay, but using this equipment, no, the kitbox PDS, for sure it is able to detect it.
Yes, that's the equipment that we have, and we basically designed it because of this. We knew that there was a problem, and we wanted to ensure that these doors are going to close when they have to be closed.
Okay, thank you, Karma. We have some more questions. Another one from Alexander Dutina. He said, hi, Alexander here. Is there any difference when fan is flowing from down to up or vice versa? And there is another explanation. I mean, when fan is located at the bottom floor or on top of the building?
Yes, that I didn't enter in detail, but there is a huge difference. Like, let's imagine that we are blowing from the bottom, that we are installing this injection point at ground floor. As we all know, in the evacuation, the door that is in ground floor will be opening and closing all the time. And once it's opening, it can create, let's say, a short path from the injection point directly leaking to the outside because this door is open. So the position, like, we really have to think about that, like, where do we want to install it? But for sure there is a difference, and if we install it on the roof at the top, the air will just be supplied through all the staircase, and we will ensure that we don't have this leakage just directly to the exit door.
So huge difference. Okay, Karma, I have another question for you from Basileus Anthis. He said, can we pressurize the lobby from the staircase pressurization fan with an air transfer damper on the wall between the two?
No, in this case, for the pressurization of the lobby, we need an equipment that is just for the lobbies.
So the equipment should be different for the lobby and the staircase.
Yes, in these cases, we need two different equipments. One that is only for the staircase and the other one that is going to be only for the lobbies.
Okay, thank you. Another question from Nathan Bewire. Hello, for the case of a smoke evacuation from the staircase, what parameters should be taken? So we are not talking about the smoke evacuation, no, in this case.
No, in this case, no, I'm sorry.
So is another, should be another strategy. So today we are focusing in the pressurization, and
Yes.
of course the extraction should follow another parameters. If you want, Nathan, we can discuss later. Okay, we have another question from Ermir Joka. Please, one question. What is the maximum number of floors that can be supported by a system?
If it's a system, it can be as many floors as you want, but of course we have to ensure that this supply air will be supplying uniformly through all the height of the building. So of course it's not the same having a building of 10 meters high, 30 meters, or even 60 meters high, which in this case we recommend to install more than one equipment and to divide it between the floors.
Okay. More questions. So the topic is interesting, I think, Karma, because we have so many questions. Another from Son Ruth. Is the calculation for a lift shaft pressurization different from a stairway pressurization?
If we are just pressurizing what is the lift, then yes, it's going to be different. Because when we are doing the pressurization of the staircase, we will just be considering what is the doors closed or the doors open, but in the lift shaft, the calculations are different. What we have in QuickFan is that you can already implement that there is a lift for the firefighters, and you just put all the parameters and they will calculate it. It's basically in one calculation, you consider both systems, but then the selection of the fans, it's different. You also need 2 fans.
Okay. Okay, more questions, Karma. From Ahmed Saik, there is an standard to be followed on the number of pressure sensors used, or is it purely basis on the response time that we want to improve?
Sorry, can you repeat it? It's the number of pressure sensors.
Yeah, it's yes. Asking if there is a standard about the minimum number of pressure sensors you.
No, as far as I know, there is no standard regarding the pressure sensors that we have to install inside the staircase.
Mm-hmm. So we are following the best response, no, of the equipment.
Yes.
Okay, more question from Franco da Silva. Good morning. When we don't have a lobby section between the pressurized staircase and the hall of the apartments, do we have to pressurize the hall as well, or could it be separated?
If we don't have the lobby, that means that there is the staircase that goes directly to the hall accommodation area. It doesn't need to be pressurized. We are just pressurizing the staircase.
Correct. I think Emir Joka is continuing questioning about the example of the number of stories.
Okay.
He's asking, for example, if I have a 45-story building, can I keep it on a single system, or does it need to be divided into zones?
I would say that when we are talking about the building that it's a high-rise building, more than 30 meters, we should start thinking about dividing the airflow into different equipments.
Okay. So generally speaking, 30 meters, no?
Yes.
Okay, another question from Tiago Pinto. He said, hello, where will the pressure sensors of the hall be installed? Should they be installed in a fire protected location?
Sorry, the smoke detector of the?
Yeah, no, the pressure sensor.
The
Where
pressure
will the pressure sensors of the hall be installed? Should they be installed in a fire protected location?
Yes, I'm assuming that the pressure sensors of the hall, I didn't talk much about halls, so I said lobby or a staircase. If we are talking about the lobby, it can be in the walls, in any place that you wanted, one inside and one it has to be outside for the difference in pressure. And if it's the staircase, it's just the same thing. It has to be one inside and one outside, but there is no specific location.
Cool. Okay, Karma, we don't have any more. Yeah, it's entering another one. Okay, we have time for one or two more. There is another from Kasil Governance. What if the lobby and the lift shaft is combined with the space staircase? Do you need to pressurize both the lift shaft and the staircase, inclusive the lobby?
No, in this case, if we are using the new standard, this one, the 13th of 2022, if the lobby, it's a firefighters lobby and it's outside, we have to consider. But if we are just talking about the service lobby, about the service lift, and it's inside the staircase, we just need to account in the calculation that there is a staircase, but we just need to account that there is a lift, but we doesn't need to consider the pressurization. It's just that there is one more door that it might leak. And this we have to consider, but not the pressurization of the lift shaft.
Thank you, Karma. Okay, we have time for another question from Fogger Kuku. He's asking if the Kitbox PDS Smart can be used for everyday ventilation as well, and if does it help reduce the stack effect in high-rise building?
That's a really interesting question. About the daily ventilation, I don't know the requirements of the daily ventilation. I'm just in the smoke part of it.
Probably the total flow it's too high for a daily ventilation of a normal staircase, because in the case of the pressurization, we need to be sure that we are generating the pressurization and the air velocity. So probably it could be tricky to use it for daily ventilation.
Okay.
But we can we can make make the question for our project department, and for sure let's see if we can use it.
Yes. And then there was another question that, well, the second part that a high-rise building considering the stack effect. There is a lot of studies that are trying to figure it out what would happen. For now, for what I have read, is that the stack effect will be there, and a way to try to overcome it is by the pressurization, but with multiple injection points. That means that more or less every 3, 4, 5 floors to add the injection point inside the staircase. So in that case, you will ensure that you have a uniform differential pressure inside the staircase.
Thank you, Karma. I think we don't have any more questions. Thank you so much for being here, everybody. As you know, we are continuing with our micro-learning program in the following months, so stay tuned to the next training sessions. Thank you, Carmen, for the nice presentation and the nice answering, and see you soon.
Thank you.
Thank you. Bye-bye.
Bye.